Okay, this is part 2 of the eCHT demo. We'll talk today in this part about the computation of chain maps between modules. Okay, so remember I, J, and E. I includes the sixth suspension of the module M1 into M. Those are the top two cells you see there. And the cofiber, or the quotient of that, is M4, the bottom two cells here in M. And we have I and J here. And then we have one more map, which is the extension cocycle, which gives the boundary map from M1 around to M4. And that's going to compute the boundary map from suspension 6 of cofiber 2 around to the suspension of cofiber new. So if you look down here, you see that the geometric degree here of S comma T minus 6 is T minus S minus 6. And then we go to T minus S minus 1. And so that's a degree 5 map here. So the first two are easy. The map definition files for I, J, and J are simple, and then E takes a tiny bit more work. Once we've created these files, we'll install them using the command new map. We'll use do lifts to compute the lifts of the chain maps, and then we use collect to collect all that data into a form that we can read easily. Okay, so the cocycles defining I and J are very easy. First, J. J maps M to M4, and the cocycle corresponding to that is just the projection from the degree 0 part of the resolution of M composed with the map from M to M4. Now, module definition files have the format cohomological degree, internal degree, domain, codomain, name of the map, and the number of generators that are mapped. Now, remember, M is cyclic, so C0 is a single copy of the Steenrod algebra. So there's only one generator, C0, to map. So this has got to be 1 here. Now, the remainder of the file then tells where the generators are, which generators are mapped, I should say, and where they go. So the only generator that is mapped is the 0th generator, the first generator in the list. And it goes to the bottom class in M4. Now, remember, if we go back to M4 up here, and remember, the bottom class in M4 here is generator number 0. Okay, so that's where it goes. And so this says then that generator number 0, C0, goes to a sum of one term, which is generator 0, and then acted upon by the only element of the Steenrod, non-zero element of the Steenrod algebra in degree 0, namely the identity map. The way to read this format is explained in that archive paper that John Rognus and I posted when we put up the database on the NIRD database archive. Okay, so that's the module definition file for J. Now for I, what are we doing? That includes, well, actually, I've taken the adjoint here. The map I actually went from the suspension 6 of M1 to M. I don't want to create a new module M1, suspension 6 of M1. So instead, I will go from M1 to suspension minus 6 of M. That works just as well. Again, the cocycle defining this map is simply the composition of the first step of the resolution, the epimorphism from D0 to M, where D star is the resolution of M1. I mean, D0 to M1, where D star is the resolution of M1, with the homomorphism. Okay, so the cohomological degree is 0. We're starting from D0 here. The internal degree is the internal degree is minus 6. That's the suspension minus 6 of M. Okay, so 0 minus 6 is, so here says, and then M1M says we're going from cohomological degree 0 of M1 to suspension minus 6 of M. And then I is the name we're giving this map. And again, only one generator is mapped because this is cyclic. That generator, number 0, goes to one term. This time it's generator number 2 in the module M. Okay, so let's go back briefly and see that. Here's generator number 2 in the module M. This 4-cell complex or 4-dimension 4 module is M. And generator number 2 is where the bottom cell of M1 gets mapped to under the map I. Okay, so that's what that definition file is going to look like. Now, the next one is the cocycle, which defines the extension here. Okay, sorry, I've reversed the arrow direction of the maps, but M4 at the right here, M in the middle, suspension 6 of M1 at the left. This is the extension we've got. The extension cocycle is simply what you get by lifting the map from M4 to M4 over the resolution out to stage 1 here. Okay, so what's going to happen here? E0, again, M4 is cyclic. E0 is going to be a single copy of the Steenrod algebra. That's going to have to map to the bottom class in M, because the bottom class in M maps to the bottom class in M4. That's where the generator in E0 goes in M4. Okay, so then think about E1. Well, E1 mapping to E0 here is going to have to kill off square 1 and square 2, because those are 0 in M4. It won't kill off square 4 because square 4 is non-zero in M4. And in fact, at this point, maybe we want to go look at the definition, at the differentials for M4 here. So let's do that. Now, if I look directly at the differentials in homological degree 4 that the machine created, they're a little ugly to read. Here, diff 4, that's, I'm way too far out. I want 1. Okay, let's, there we go. That's more like it, diff.1. All right, so these are still a little bit ugly to read. So there's a nice little program called convert. And it'll take these differential files and convert them to one that's written in terms of the Milnor basis. It's a little easier to read. So I like to call this HDiff.1 for humanly readable diff.1. The format of these files, and this is explained in the archive paper that I mentioned, is 211. There's a header at the top that has 2 entries in it that says there are 7 generators and it's complete through internal degree 40. Then it has blocks which have one header for each block. There's a 1 here, there's a 2 down here, there's a 6 down here. Each of these blocks has a header consisting of 1 term. And then the third one says there's 1 element in each block. Okay, so that's this element. See, there aren't any elements with more than 1 term, but if we look up here, you see here's a block that has 1 element, but it's got many terms in it. It has 7 terms there. Okay, so that's what we're going to do. And then the last term, I here says, write it in internal, that is Milnor basis terms. Now, if I look at HDiff.1, I can see what this map from E1 to E0 down here looks like. The map, the differential from E1 to E0 is displayed here. Getting it highlighted though in Beamer is almost impossible, so we won't bother with that. Generator number 0 is in degree 1, it goes to square 1. Okay, well that's, we mentioned already, we had to kill square 1. Generator number 1 is in degree 2, it kills square 2. Okay, that we kind of saw too. Now the next generator goes to square 6. And then after that, the generators are in degree 8 and higher. If you think about M, it's top cells in dimension 7. So they're clearly, and suspension 6 of M1, its top cell is in dimension 7. So clearly generators in degree 8 and higher aren't going to matter. So in fact here, this generator number 2, 0, 1, 2 that hits square 6 is the one that matters. Okay, so generator number 2 in E1 maps to square 6 in E0. Where's that in M? Well, if we go back up to the exact sequence here, square 6 on the bottom cell of M is exactly generator number 2 there. Okay, so let's go back to the extension cocycle here. That says this generator goes to the degree 6 class in M. Now, The extension cocycle from E1 to M1 has to actually hit the class in M1 that hits that, and that's the bottom class. So that's generator number 0 in M1. Okay, so here's how you say all of that in a map definition file. Okay, cohomological degree 1. Okay, that's going from E1, the first stage of the resolution, not the zeroth. Internal degree 6. Okay, so that is all visible in E1 mapping to suspension 6. Okay, then the domain is M4. Well, that's because we're looking at the resolution of M4 here and mapping to M1. The codomain is M1. We're going to call the map E. What does it do? It maps generator number 2 in E1 in the resolution of M4. Okay, so we saw that back here. Generator 0 and 1 map trivially. Generator number 2 is the one that maps non-trivially. And that goes to the bottom class in M1. So one term and generator number 0. And then the identity element of the Steenrod algebra acting on that. Okay, so that's all we have to do to put in that. Okay, so let's now create those and create those maps. Okay, so we go back up to A, and then let's do I first. And let me go back up here so I actually have the file in front of me so I don't mistype it. Okay, so vi.def, I'll just call it i.def. Okay, so the first line, now this is important. The first line of the map definition file needs to have these 6 things in it: S, T, domain, codomain, map name, and number of generators mapped. Okay, so in this case, that's 0, -6, M1, M, maps name is I, maps one term non-trivially. That term is generator number 0, and it goes to something with one sum of one term, which is generator number 2, acted upon by the identity element of the Steenrod algebra. Okay, so now new map i.def. Here in the new map command, all you need to do is to give it the map definition, because everything it needs to know is in the map definition itself. Okay, so here we go. It says it created M1/maps, put the map I in it. It's ready to compute lifts. You go change directory to M1. Add I to your maps file if necessary. Well, we're going to use the maps file it generated, so we don't have to do that. And then we run the script do lifts. Okay, so let's do that. Go down to M1./do lifts. Now this runs by cohomological degrees. We're just going to do them all, 0 through 60. And files we want, the maps we want to lift are the maps in maps. Let's look at file maps here briefly. I is the only element in it. Okay, so we're just doing I. If you sometimes want to, often you'll have a maps file that has many more things. In the third video, we'll see an example where maps files could have a lot more things in it. Okay, so do lifts from 0 to 60 and do it for the maps in the maps file. Now, I'm not going to put this in the background because this is very talkative and we wouldn't be able to do anything else in the meantime, and it's very fast. Okay, so it's talking a lot here. You see little things, sort of error messages popping up back here. Those are done. Those are happening because we're trying to map degree 42 to degree 42, but the resolution has only been created out through degree 40, and so it's not able to do that. So it computes everything it can compute. So this is one thing you have to watch out for. If you extend your resolutions, then you need to extend the maps. So you have to go back and rerun do lifts again. It doesn't, when you extend a resolution, it doesn't look around and say, what are all the maps that were involved here, and extend those automatically for you. That's left up to you. Okay, so now let's collect all this. Oh, let's actually just briefly look at the maps file here. The maps file is just called I. And actually, let's look at it with a bit more resolution. Okay, so in here you see the definition. That's the one we gave it. Okay, so that's the maps file we handed it. The map itself has the entire chain map that it computed in here. So there's a lot of stuff here. the map.aug, that is created by composing with the by modding out the augmentation ideal. So all of this, all that map.aug keeps track of is the action by the square 2 to the i's. And that's actually useful in computing brackets and the like. And these files, brackets and brackets.sim, contain information about the brackets there. And map.aug also contains information. I'm sorry, map.aug only contains information about what's happening to the resolution after you mod out by the augmentation ideal. So it's telling you the induced map in ext, and it's brackets that will tell you the induced, tell you about the brackets. To read about the brackets, go look at the archive posting that has full detail in there on that. Okay, so this, we don't want to read this map.aug though, even though it's not a terrible thing, because it's really just kind of a bunch of numbers here. So instead, what we'll do is use this program collect. We'll collect it into all.i. This is telling us what the map I does. Okay, so now let's go back and compare this to what we see. Remember what I did. It included the M1, this bottom module down here, the cofiber of 2, into M, and then computed the chain map induced by that. What happens when you apply ext? That gives you the induced map from ext of M to ext of M1. Okay, so what we're going to see here is I applied to generator number 24 in M is going to go to generator 22 in cofiber 2. Okay, so 24 in M is out here, cohomological degree 2, generator number 4. Okay, so this is in degree 12 here. And that's going to go to 22 in M1. 22 in M1 is back here. Okay, that's in degree 6. Well, that's just right. This was a map of internal degree 6. So something of internal degree, well, actually, this is internal degree 14 going to something of internal degree 8. But geometric degree also changes by 6. So degree 12 goes down to degree 6. And then generate H2 times that, that's going to be generator number 4 in the homological degree 3 up here, must then go to 3, 3 here. Let's see. Yes, there we go. We see that using the, okay, there we go. 3, 4 in M. I sent 3, 4 in M to 3, 3 in M1. Okay, so that's what that map looks like. Now go back up to the Steenrod algebra directory and create the definition file for J. Okay, so what's that look like? 0, 0, M to M4. We'll call it J. There's one term. 0, 1, 0, 0, 1, hex 80. Okay, that's the map definition file for J. And we install this using new map, j.def. Okay, so now we change the directory down to M. Notice it's kind to remind you where you want to be. Okay, we go down to M and run do lifts, like we did before. Okay, now this doesn't do any. This is an internal degree 0 map. So we didn't get those errors saying that we couldn't map something here. The reason we got them back here for M1 was that we'd computed M1 through internal degree 60, but suspension minus 6 of M was through degree 40, I mean. It was computed through degree 40 minus 6, only 34. So things in M1 of internal degree beyond 34 had no place to go to in M. We hadn't computed that yet. Okay, so this is done now. So we'll collect the results, collect maps all.j, and then have a look at that. And we see now, let's make this a little smaller. Okay, spread it out. Okay, there we go. Now this is going from M4 up here in eCHT. It's going from M4 up here at the top to M in the middle. Okay, so 0, 0 in M4 goes to 0, 0 in M here. Okay, so J of 0, 0, 0 is this generator here, and it goes to 0, 0 down here. Okay, so this does pretty much the things you'd like to see, but notice generator number 1, 2 here. 1, 1 got in M4 got mapped, 1, 3 in M4 got mapped, but 1, 2 in M4 did map trivially. It's not mentioned because it went to 0. So this only lists the things that go non-zero. Notice 1, 3 in M4 goes to 1, 2 in M. Okay, that makes sense out here. 1, 3 in M4 is this sigma in degree 7, and it goes to sigma in degree 7 here, but that's generator number 2 because it's intervening cell that came by the boundary map from the cofiber of 2 isn't here in M. Okay, so you can read through here and see exactly what's happening, and it's particularly helpful in bi-degrees, like up here where you have 2 things mapping, and well, it's pretty clear what's going on. But getting out into higher degrees, it's very helpful to have this to tell you exactly what the map looks like. All right, so that's that one. Now let's go create the extension cocycle. Back up to A and vie.def. And rather than reimagine how to do this, I'll just read what I had typed here. Okay. 1, 6, okay, cohomological degree 1, internal degree 6 goes from M4 to M1. The map is called E, maps 1 generator non-trivially. That was generator number 2, and it maps to 1 term consisting of generator 0 acted upon by the identity map of the Steenrite algebra. Okay, so now new map, e.def, and okay, so now it's set everything up. We changed directory to M4. Remember, that's the domain. Oh, map files are always create the subdirectory containing a map is a subdirectory of the directory which contains the domain module. Okay, so, and it tells what its codomain is, of course. Okay, so go down to M4 /do lifts 0 to 60. Now this has got a cohomological degree 1 shift in it, so that'll generate a few error messages because one of these resolutions has been computed a bit further than the other. That doesn't hurt anything. You should always compute your resolutions a little further than you want to examine the chain maps, just so you don't have to be too fussy about that. All right, so there we go. Okay, so. Okay, the shapefile was only good through filtration 60 and we needed filtration 61. Well, there we go. We started over here in filtration 60 for M1 and it tried to map to filtration 61 and M4 and there isn't one. We haven't computed that yet. So if we had wanted one, we'd have had to run M4 out through 1 homological degree greater. Okay, so now /collect maps all.e and let's look at all.e to see what we've got. Okay, so now we'll go back and look at the resolution we had here. Okay, so now we might want to roll this around a little bit more. Okay, so 0, 0 in M1 here, first entry, 0, 0 in M1 goes to 1, 2 in under the map E. Okay, so 0, 0 in M1. Okay, down here in M1, 0, 0 is the generator in degree by degree 0, 0. Homological degree 0 generator number 0, and it's going to go to 1, 2 up in cofiber new. Okay, homological degree 1 generator number 2. Ah, there we go. That's that little lightning flash here that we saw did not map into BO1. Okay, so it's exactly hit by this lightning flash in cofiber 2 that came around and hit it. Okay, so now generator 1, 0 in M1. Okay, so that's what? That's H1 on the bottom cell here. That goes around and hits generator number 2 in M4. Okay, 2, 2, I mean. Okay, so cohomological degree 2, generator number 2, there it is, H1 on the beginning of that lightning flash. And so you can run through here and see exactly what the boundary map in eXT from cofiber 2 up to cofiber new looks like, defining BO1 here. Okay, in the next section, we will see how to also compute the action of X over A of F2, F2 on all of this.